Good morning, everyone. So, looks like most of you probably will choose to attend the later class, which is fine. Right, so we're just going to start slowly. We are on the linear transformation topic. So the chapter 1, which is topic 1 on the systems of linear equations, but we have finished both the lecture and the tutorial. Right, but then the concepts that we covered will still be recovered in the later topics. Okay, so solving of linear equations or systems of linear equations, they are so fundamental that we apply them in many applications as well as more advanced techniques in mathematics, as you'll see later on. So then now we look at the concept of the linear transformation. So last week we covered that linear transformations are just fancy way of saying you just do something to the vector. Okay, so or more generally we say that we do something to the vector space. Okay, because what is a vector space? Right, the vector space is just a space of vectors. Right, so a space, right, like for example the 2D plane here. Okay, so the 2D plane here can be so-called spanned by any two non-parallel vectors. Okay, so in fact, two non-parallel vectors, you can choose, of course, any two non-parallel vectors to kind of span the plane, meaning to say, if you do like, for example, one vector multiplied by a constant plus another vector multiplied by another constant, then actually you can go to any point in the space, right? So the concept here is, let's say I give you a point in the space, let's say for example 1, 2. Okay, say come to this position. Now I say I'll come to this position, actually the idea very simple. You can actually walk 1 unit in x and then 2 units in y, right? Then you'll come to this position. Okay, but that's not the only path you can take. There are so-called infinite paths you can take. Because you can always say that, oh, I can also do like, take this vector in this direction, then after that walk in this direction. Okay, I can come to the same point, right? So which means that as long as I give you any two non-parallel vectors, right? For example, this is the third one, right? As long as I give you any two non-parallel vectors, you can just do like a v1 plus b v2 equals to any vector, let's say, say u, okay? So a v1 plus b v2, you can reach any point in space. Okay, so any point here, right, for example, will be like, say, this point here, whereby u, right, is equivalent to, in this case, 1, 2. Okay, so just an example, right? So as long as you choose v1 and v2 such that they are not parallel, you can span so-called the 2D vector space. Okay, that's what we meant by vector space, right? You can basically go to any point in that space, right, by having a linear combination of vectors. Okay, so what's the deal with this is that linear transformations, they just apply some changes to the input vector such that they become another output vector. So the concept of the linear transformation is just trying to manipulate vectors, that's all. Okay, so then the vector space that is being manipulated, how it is being manipulated can be in a linear fashion, can also be in the non-linear fashion. Okay, so linear means it must satisfy the two conditions here. Okay, so these are the conditions required for what we call a linear transformation or transformation to be linear. Then last week, some of you asked me, right, what is a non-linear transformation? Non-linear transformation will be one such that, right, you cannot satisfy the two conditions here, okay, or either of the two conditions here. For example, a non-linear transformation can be something that looks like, so let's say, or v, right, equals to, for example, k times v square. Okay, so kv square, for example, right, is not a linear transformation, right, because you notice that you cannot sub in v1 plus v2 into the square here and then expect it to follow this equality. Okay, so there are nonlinear transformations, right, but of course they are not so-called that useful or maybe common, so therefore we just stick ourselves with the linear transformations. Okay, and then thing about linear transformations here is that it sets the stage for a very important application coming up later today, which is the thing we call eigen decomposition. Okay, just fancy way for saying, right, you just factorize the matrix. Okay, factorize the matrix in a useful form. How useful is useful, right? Later on we'll see. Okay, so we have looked at some examples of the linear transformations already. Okay, and then I think we stopped at determinant, right? Yeah, we stopped at determinant. So determinant is just a jargon, right? A terminology, a name given to the so-called space scale factor of a linear transformation, right? So for example, this matrix here, right, which represents a linear transformation, so-called matrix, you can actually find out that the determinant is -4, right? So what happens is that it is trying to expand the vector space by 4 times, as you can see from the drawing here. Okay, so what happens is that if you want to know what the linear transformation is doing or what's the determinant visually, right, you can simply just draw out the vectors or the column vectors in the matrix itself, and then subsequently compare the input vector space to the output vector space. Okay, so this is something like because when you transform the unit vector I, right, it becomes 2, 0. So therefore you can see that the unit vector I has been so-called elongated by 2 times. Okay, and then the same goes with the j vector, right? Because the j vector has been flipped, right? It's been flipped across the x-axis, vertically, that is, right? And also be elongated by 2 times. So therefore, right, what happens here is that the vector space has been expanded by 4 times. Okay, but at the same time it's flipped. So therefore the negative sign represents the flipping of the vector space. The 4 represents the expansion 4 times of the vector space. Okay, so that's how one can identify the meaning of the determinant. Okay, so that's the meaning of the determinant. But of course, at this stage, we didn't kind of explain how the determinant process or how the determinant calculation comes about. Okay, so it comes about because of the inverse of the matrix, right? So we also looked at the determinant of a 3x3 matrix, which is just the scale factor of the volume, okay, of the 3-dimensional volumetric space, right, of the vectors. So you can see here with the kind of drawing here, right, you can see that after you skew this cube, if you skew this cube and then pull it to the right by 2 times, then logically the vector space must expand 2 times, what, right? So you just skew it and then you expand it, like you extrude it by 2 times. So therefore you can see the determinant is 2. Okay, and last week I got some questions, and that is, right, what's the deal with this operation here? Okay, the truth is, the operation here is just an example when you choose the first row as the pivot. Okay, so there's this plus minus plus thing going on, right? Of course, how this operation comes about is in the definition of the inverse when you perform row operations. Okay, so like, let me repeat this. So if I choose the first row as the pivot, right, meaning to say I take the plus A, this plus A, then after that I take so-called the subdeterminant, right, by covering up the row and column of A. So you can see row and column of A I cover, right? Then after that I just take E times I minus H times F. So like the determinant of so-called sub-matrix, okay, like portion of the matrix by covering up the pivot element here. Okay, then the same thing goes with minus B, you can see, right? Minus B, then you cover the first row and cover the second column because that's where the B element is, and then you take the sub-determinant. Okay, so you can take D times I minus G times F, and just repeat for plus C. Okay, so because you clearly observe that the A, B, and C, which is the pivot elements, will show up in the operation here. So therefore, it makes total sense, right, to just choose a row with more zeros. Okay, so for example, if you choose the first row here, you got 2 zeros here. So then it makes sense because you just have just need to expand 1 only. Okay, you just use the pivot 1, right? Then multiply 1 time on the sub-determinant, you get the total determinant already. Okay, so therefore, it kind of makes sense, right? If you want to choose the pivots, right, with less zeros, you can, right? Let's say, for example, if I go and choose which one? The second column. Okay, second column only got 1 0, but let's say you prefer to use that, right? It's totally fine, right? It's just that you have more operations here, but you still get the same determinant. Okay, so the determinant does not change no matter which pivot you use, right? Okay, so just choose one with more zeros and then your life will be certainly a lot easier. Okay? So then later on we will have something to say about the determinant, right? Because the determinant can be 0, and when the determinant is 0, actually it kind of says something about the transformation. Okay? Yeah. So then we also covered the initial part of the inverse of a matrix, which is coming from the inverse of a linear transformation. So the inverse very easy to understand in the sense that if you take the matrix and multiply by its inverse or vice versa, you must get the identity matrix. Okay, you must get the identity matrix. So therefore, the inverse of a linear transformation graphically also makes total sense. Basically, what A inverse is trying to do is to undo matrix A, right? Because A times A inverse equals to I, right? So which means that I multiplied by any vector is not doing anything. Okay, if you take identity I times any vector equals to the vector itself, right? So that means I is like a useless matrix, right? It's not doing anything. Okay, so how can I be not doing anything? Then you must undo lah, right? Whatever you apply, right, to the vector, you must undo it, then after that you can get I what? Okay, because it's like you're not doing anything to the vector space, right? So therefore, in this respect, we can understand the inverse graphically. Okay, so if you have a 90 degrees clockwise rotation, right, then after that you will have 90 degrees anti-clockwise rotation for the inverse. Okay, so whatever a matrix does, right, its inverse will undo. Okay, so logically, what is the inverse of A inverse? What is the inverse of A inverse? A lah, correct or not? So A inverse just equals to A lah. Okay, because you inverse because like for example, if the inverse is anti-clockwise rotation, then of course the inverse of this inverse must be the clockwise rotation, right? Okay, so I hope that makes sense. Yeah, so this is where the determinant of the matrix is being derived, okay, which is using row operations or Gauss-Jordan elimination to obtain the inverse of a matrix. Okay, so this is something that we have kind of conceptually covered, although I didn't exactly go through the row ops in detail, right? But the idea is straightforward. Now, because you are solving AI in the augmented matrix, so this matrix here, right, originally, let's say you are solving AV equals to B. Then what happens is, in your row ops, you put the augmented matrix as A slash B. Then A slash B, you perform row ops such that you get I slash V. Okay, so if you compare like the positions of the equations that you are trying to solve. So now you're trying to solve A times A inverse for I, right? So what happens is that A and B, the first and the third element, you put it in the same order. So then you have A and I, right? First and third element. Can see, right? So if you perform row ops, right, you are going to get I and A inverse. Now notice that A inverse takes the location or takes the position of V. Okay, A inverse takes the position of V. So when the left-hand side matrix becomes I, then the right-hand side must become A inverse. So this is concretely demonstrated in these row operations. Okay, so A inverse is on the right side when you make the original matrix A become I. Okay, so then we notice from here, we have 1 over AD minus BC in all the terms in A inverse. So then we define that as the determinant. Okay, and then we also notice something very interesting, and that is, right, what is the meaning of 1 over determinant? 1 over determinant is if you expand, for example, the vector space twice when you multiply by A. So you can observe that if let's say the determinant of A, let's say is 2. So this means that you expand vector space, so-called the area by 2 times, correct? Okay, so that's what matrix A is trying to do, right? Expand the vector space area by 2 times. Okay, but then what is the determinant of A inverse then? What is the determinant of A inverse? Now the determinant of A inverse must obviously be 1 over 2. Correct or not? Because it's trying to undo what? What matrix A is trying to do. In order to undo it, the vector space must be halved. So therefore, this is to contract the vector space area back. Okay? So what is this determinant of A inverse? It has to be 1 over the determinant of matrix A. This half, right, has to be 1 over the determinant of A. And this makes logical sense graphically. Okay? So therefore, you see this 1 over determinant of A right here. Right? 1 over determinant, because I need to undo what matrix A is trying to do. Okay? So that's what the inverse is trying to do. Okay? Then of course, it has to multiply by a matrix. Then the matrix here, right, is called the adjoint or adjugate, okay, of the matrix, right, which is called the transpose of its cofactor matrix. For 2 by 2, this adjoint matrix is very straightforward. Okay? Now if you look at the thing here, right, you really just swap the diagonal elements and then you throw a negative, right, to the off diagonals. Okay? So if you didn't realize, right, like matrix A is A, B, C, D, right? So what's the adjoint or adjugate matrix here? You swap A and D. Then after that, you put a minus, right, to the off diagonals B and C. Okay? So that's what the row operations tell you. So 2 by 2, the matrix inverse is easy to define. Okay? So you no need to go and do the row operations painstakingly, but instead we just use the formula directly. Okay? But however, for 3 by 3, it's a pain. Okay? It's a pain. So, but before we look at 3 by 3, maybe we look at this example first. So let's determine the inverse of matrix A and verify using the definition of the inverse. Now in layman, what does the inverse of A do? Okay. So what's the deal with this? Oh, okay. Determine the inverse. Okay. So inverse, straight away calculate A inverse equals to 1 over the determinant of matrix A multiplied by the adjoint or the adjugate of the matrix A. So then this guy, 1 over determinant, right, straight away put inside the formula. So this will be 2 times 1 minus 0 times 1. Okay, then the adjoint, as I mentioned, you just swap the diagonal elements. So 2, 1 become 1, 2. 2, 1 here become 1, 2. Then after that, you just throw a negative to the off diagonals. Diagonal, off diagonals. No, negative must be given to both off diagonals. Minus 0 is still 0, correct? Then 1 become minus 1. So therefore, you can see here, right, it's just half multiplied by this matrix here, by the adjoint matrix. Okay, so this is A inverse. So next, in layman, what does the inverse of A do? What does the inverse of A do? Okay, so the inverse of A is to undo the transformation caused by matrix A. But what is the transformation caused by matrix A? The transformation caused by matrix A, if you realize, is what? So 2, 0 is this vector, right? So this is 2, 0. And then the original input matrix will be I here. So then after that, it also skews because it becomes 1, 1. So this is 1, 1. So that means 1, 0, 1 become 1, 1. J becomes 1, 1. So you can see that the vector space becomes skewed. Okay? So therefore, this is the transformation caused by A. Right? But if you look at this transformation, actually what it does, so this is A inverse, Hold on, Okay, this is the transformation caused by A. Let's see what's the transformation caused by A inverse. How can it undo this? That means it must unskew, right? Or rather, you can say that it's skewed in the other direction. Then it must contract, what? Because this one elongates, right? The space horizontally towards the right. So therefore, it is logical to deduce that A inverse is going to contract the vector space towards the left. So let's see if it works out to be like that. So, okay, so it's a half here, right? So what happens is that we can multiply in the half so that we can draw our output vectors more clearly. So this one is like a half, 0, minus half, 1. Okay? So let's see what happens here. Now half means originally your I is 1, 0. Now become half 0. So if I draw I bigger, so this is my I. So you notice that it becomes half 0. Half 0 means it contracts the vector space. So this is half 0. Then your j vector becomes minus half 1. But what's minus half? So minus half is on the negative x-axis. So maybe it looks something like that. Okay, wait. So this is your j vector. Then this is minus half 1. Now you notice that it is exactly what we mentioned a few minutes ago, right? The original vector space is this vector space, correct? So this is the original vector space. But now the new vector space the output vector space looks like that. Correct or not? So you notice that this one skew right, this one skew left. Agree? Then this one elongate horizontally twice. This one contract horizontally twice. Contract by half lah. Correct or not? Okay, so let's write down. So this part, matrix A, it skews right. Then this guy, A inverse, right, skews left. So this one must undo. So this one undo. Okay? Then the other one is extends right by 2 times. Wait, my spelling is wrong. By 2 times. So then the A inverse must undo also. Contracts left by half times. So this one undo also. Okay, so I think graphically we can see the effect of A inverse very clearly. Okay, and of course you can apply to other matrices as well. If it's 3 by 3 matrix, then maybe it's not so easy to draw. Okay, but 2 by 2 we can kind of visually understand very easily. Any questions on the concept or the graphical representation of the inverse? Okay, good. Okay, so then for 3 by 3 it's a pane. Right, it's a pane. Now, the formula here, no change. Always the same formula, the blue box formula. So, determinant for 3 by 3, as you have observed, is quite a bit tedious to obtain. Okay, but what is even more difficult, or rather tedious to obtain, is the adjoint matrix. So the adjoint matrix, I just have to be careful. Okay, the adjoint matrix, you cannot, most of us cannot write it directly. We have to write the cofactor matrix transpose. So it's a transpose of some other matrix called the cofactor matrix. Okay, so what happens is this. Now what's a cofactor matrix? Cofactor matrix, right, means you, first of all, to get this element, you cover, like that. Then after that, you write down what we call the cofactor. Okay, so the cofactor is like the subdeterminant, if you will. So it is really E times I minus H times F. So that's the first one here. Okay? Can Then after you just repeat this process of writing subdeterminants for all the elements. After you write all elements, then you put the plus, minus, plus, minus, plus, minus, and so forth. Okay, so how did this thing come about? Matrix inverse. Okay, so if you perform row ops to the matrix inverse, which I think I never show here because it's too long. Okay, too long. Not important. Right, so if you do the same row ops as what is given here, but it's just that your matrix A is 3 by 3, right? Then you, after a very long, tedious process, you will realize that your A inverse has this form. Okay, your A inverse will contain the adjoint in this form. Right? So they so-called kind of condense this heuristic, right? And just straight away tell you that, oh, it's this process. Okay? So to make it concrete, let's go through this exercise. So this one, you have to really practice a few times, then you will get the hang of it. Okay? Your calculator can calculate inverse of a matrix or not? Can your calculator calculate matrix inverse? Don't know. If you can calculate the inverse of the matrix using your calculator, then that, of course, that will be a great help to you. Okay? Although you still have to show the working, right, to obtain the full marks, but at least you know where, I mean, you know what is the correct answer. Okay? So maybe that will be quite useful in the quiz or your midterms. So maybe find out whether your calculator can calculate the inverse of a 3 by 3 matrix. 2 by 2 very fast. 2 by 2 don't even need calculator, but I think 3 by 3 will be quite good to have. So let's calculate the inverse. Now, it's better to first of all calculate the determinant first. So determinant of A. So I'm going to choose the last row as the pivot. Okay, so the last row plus minus plus, right? So it will be plus 3 multiplied by 0 times 1, 0 times minus 1, minus 2 times 1. So actually the determinant is just 6. Okay, no problem with that. So then we calculate the cofactor. Okay, cofactor matrix C. Then later then we transpose, because we still need to transpose. So the cofactor, right, will be, okay, this one has to do a bit of visual blocking. So for this element 1 here, right, you block it. Then you notice that it must be minus 2 times 0 minus 0 times minus 1, which is just 0. Okay? So maybe just for clarity, I'll write out everything. Right? So minus 2 times 0 minus 0 times minus 1. Okay? Then the second element on the first row, also visually block out. And then 2 times 0 minus 3 times minus 1. Then the third element on the first row, 2 times 0 minus 3 times minus 2. I haven't put the plus minus plus yet. So just do the so-called cross multiplication first. Okay, later then we put in the plus minus plus. I think it's easier that way. Right? So first column, second row, 0 times 0 minus 0 times 1. Okay? Then we have 1 times 0 minus 3 times 1. This element on the second row, we have 1 times 0 minus 3 times 0. Then finally we have last row, first column. So 0 times minus 1 minus 2 times 1. Then 1 times minus 1 minus 2 times 1. Finally, 1 times minus 2 minus 2 times 0. So this is your cofactor matrix. Then I forgot, or rather I have not put in the plus minus plus. So this one, put a minus, 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 and there's a minus here. Okay, so there are 4 minuses, because it's plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay, so if you write out everything, it looks like that. Hopefully, I'm not sure if there are mistakes. So work out the arithmetic. So you get 0 here. Then this guy is a what? Is a plus 3, so it's a minus 3 right there. Then this guy is a 6. And this guy is a 0. This one is a minus 3. This one will be a 3. Oops, it will be a 0. This one is a 2. So this one is a 1 minus 2. So that's minus 1. So this is a 1. Then finally you have a minus 2. So this is your cofactor matrix. So now you have to transpose the cofactor matrix, right? So A inverse is 1 over the determinant of A times the cofactor transpose. Okay? So that will be 1 over 6. Then you transpose this cofactor, meaning to say a row become column. So therefore you will get 0 minus 3, 6, 0 minus 3, 0, and finally 2, 1 minus 2. So I have a mistake here. I got 1 here. So I'm supposed to get 3, is it? Is this 3? This is 3. Sorry. I think I made a mistake here, is it? Wait, 1 times 1 minus, oh, 1 times minus 1, okay. Okay, this one will be 1 times minus 1, right. So it should be minus 3. Minus 3 times minus, so become 3, yeah? So this one is 3, and therefore this is 3. There you have it, inverse of 3 by 3. Any questions on the operation? Good. Okay, so yeah, you definitely need some practice in your tutorials. Okay, if you have not done this before. So now let's look at the concept of a singular matrix. So just now I mentioned that the determinant can be 0. Okay, and indeed, this is what happens when you have a singular matrix, okay, or what we call a singular matrix. Now, a singular matrix is just a matrix that is not invertible. That's why it's called singular. Singular in the sense that, right, you can only perform the transformation in one direction. You can't go back. Okay, you cannot reverse or you cannot undo. So therefore, if you cannot undo, then it is not invertible. Okay, so singular matrix is just a matrix that has no inverse. So this guy, no inverse. That means you cannot define the inverse. But how can you not identify or not define the inverse when the determinant is 0? Okay, so no inverse means A inverse equals to 1 over determinant of A times the adjoint matrix. Because adjoint is always defined, right? It is just cross multiplication, so it's not possible for the adjoint matrix to be undefined. But 1 over determinant can be undefined. Okay? So where what determinant is 0. Okay? So 1 over determinant is undefined. Because you cannot define 1 over 0. Which means graphically, because your determinant is 0, so if the determinant is 0, means the output vector space has 0 volume or 0 area. Okay, depends on what is the dimensionality of your matrix here. So you notice that if I were to draw this matrix A, let's draw the output vectors. So now the output vector become 2, 1. So 2, 1 is 2 in X, 1 in Y, so maybe look something like that. Then the J becomes minus 2, minus 1. But minus 2, minus 1 is, oh sorry, my 2, 1 a bit not accurate. Because it's 2 in X, 1 in Y, so it should probably look more like that. So then minus 2, minus 1 is like that. It's just in the opposite direction. So you notice that the original vector space, which is your Ij, becomes flattened into a single line. So the original vector space, Ij looks like that. Correct? This is the original vector space. So you can see, this thing is collinear. So therefore, if you try to draw like an area using the two pink color vectors, you can't draw an area. There's no area, just along a line. Okay, so that means the original vector space has been flattened to a line. So let's write this down. So input vector space flattened to a line. So what's a line? 0 area. Okay, so because it's 0 area, right, so the determinant is 0. Okay, and you can of course verify, right, because your determinant of A is 2 times minus 1 minus 1 times minus 2. So it's minus 2 plus 2, so it's 0. So therefore matrix A is singular. Then the same can be said for B. B also the same. So you look at matrix B, right, I remain as I, but J has been flattened to I. So therefore the vector space is just like a line on the horizontal axis. Okay? So therefore this is the output vector space of B, also along a line. Okay? So the same goes with matrix B right here. So this one is for A, this one is for B. So if you look at the determinant of B, it's very clear that it is 0. Any questions on the graphical meaning of a singular matrix? Right? Should be pretty clear from here. Okay? So whenever you have a singular matrix, right, that transforms the vector space into a lower dimensional vector space, then you get the determinant to be 0. Okay? That is not invertible. That means the matrix is not invertible because you cannot have 1 over 0. Okay? So now the demonstration here is for 2 by 2 matrices, but for 3 by 3 matrices, it's also a similar concept. Okay, but in this case, the flattening, right, can be a volume into a plane or a line. Okay, that means the volume is no longer a volume, right? So if you look at for matrix A, let's calculate the determinant. All right. So I think the easiest is maybe this row, or you can choose the second this column, or you want to choose the second row as well, also can. Okay, so I'll just choose this. So therefore you can see that the determinant of A, so that will be 1 multiplied by 1 times 1 minus 8 times 2. Okay, wait. Minus 0, then plus 3, made it in time. Minus 1 times minus 1. Okay, so the determinant of A is really just, wait, let me see. 1 minus 16, right? So that's minus 15. Then this is 3 times, what's this? 5 plus 15. So you get 0. So once the determinant of A equivalent to 0, then A inverse do not exist. Can I? That means undefined. I use do not exist and undefined quite loosely here. Okay, they represent the same thing. So then for B, inverse of the matrix. Okay, so maybe just now I have a demonstration for the inverse of matrix B, for the inverse of a 3 by 3 matrix ready. So maybe you guys take some time to practice this while I'll mark your attendance. So this one, try. Okay, try now to get the inverse. Alexander? No. Aliyah? No. Emelina? Angelico? Sean? Jiaxuan? Brian? Chen Chang? Zhen Yi? Ivan? Ivan Chow? Yang Ing? Emilia? Erwin? Yanjing? Zhan Yang? Zhan Yang? Sorry, Yanjing here, no? Yanjing. Okay, sorry. Dongbing? Wait. I shouldn't put absent, because maybe they joined the later class. Okay. Yeah, Norita Su is here. Xavier is here. Joey, Jordan, Kayla. No. Kevin, Ken Leong, Sharon, not here yet. Dawson, Chen Ying, Jonathan. No. Kun Yong, Mac, Mikhail, just right. You time it perfectly. Mohan, Azari, Danish, Afan, Naya, Nitin, Ding Jie, King Hong, Zixuan, Fadila, Phoebe, Yan Heng, Sherwin, Benjamin, Raymond, Reese, Ruji Ratanalai, Jun Pang, Jerome, Sean, Justin, Hao Bo, Ryan, Suhadi, Johans, Wei Yan, Yi Zhong, Tamsen, Trisha, Hong Tan, Shi Kang, Xing Zhi, Zotet, Zunping Wai. Okay. Wait up. Where? No? You just calculate the inverse only, right? Right. Okay, so before I proceed to find the inverse of matrix B with you, you can verify the determinant of matrix A being 0 from this plotting here. Because if you look at matrix A and you try to plot out the column vectors, so the column vectors are the output vectors of the linear transformation. So 1, 0, 3, 2, 1, 8 and minus 1, 2, 1. Okay, so if I were to plot it out in GeoGebra here, now you notice that, right, the three vectors, they form a plane. They only span a plane. You see, the three vectors, okay, but if I were to rotate it like to a nice position, you can see, right, the three vectors actually lie on one plane. Okay? So therefore the vector space, the original volumetric vector space by ijk, spanned by ijk, has been flattened into a plane. Okay? Can you see the output vectors here? So output vectors span a plane. Right? So because the output vectors span a plane which is one dimension lower than the 3D vector space originally, so it flattened the volume into a plane. So hence the determinant of A must be 0. Flatten from 3D volume space, volumetric space. So determinant must be 0. Okay, so can also span a line, right? Certainly if the columns of matrix A span just one line, then also flatten, flatten into 1D, 3D flatten into 1D. Okay, but this one 3D flatten into 2D. Right, as long as flatten into a lower dimensional space, then it's considered not invertible. Okay, so let's look at matrix B. Hopefully you have tried that on your own already. So just now I got a question. How do you get the inverse? Now first of all, you get the determinant first. If the determinant is 0, then there's nothing else to do. Okay, you just say that the inverse doesn't exist, right? Or it's not defined. But then do not straight away go and get the cofactor, because that could be a waste of time if the determinant is 0. So therefore, calculate the determinant first, right? Work smart, so-called. So therefore, I'm going to choose the first column once again, okay, because it has a 0 here. So therefore, you'll be minus 1 multiplied by 4 minus 2, then plus 0, no need to write. Then after that, you have a plus 3 multiplied by 4 minus 1. Okay, so therefore, in this case, it looks like you're going to get 2 minus 2. So therefore, this will be 3 times 3. So the determinant is 7. Is that correct? So after you get the determinant is non-zero, so therefore B inverse will exist. B inverse will exist, right? So therefore, now you need to get the adjoint of matrix B. So the adjoint of matrix B, you get the cofactor first. Okay, cofactor matrix of B, right? So then, remember, I'm just going to make the cross multiplication first. Okay, then I put minus. So I straight away do. So therefore, this will be what? 1 times 4. So this will be a 4 minus 2. Okay, then this will be a 0 minus 6. Then this guy will be a 0 minus 3. Then this will be 8 minus 1, then minus 4 minus 3. This guy will be minus 1, minus 6. This guy, 4 minus 1, minus 2 minus 0, and finally is minus 1 minus 0. Okay, after I have this, then I must remember to put my negative sign. So then I work out the answer, which is 2, 6 minus 3, minus 7, minus 7, 7, 3, 2, and minus 1. Okay, so this is the cofactor. Then B inverse is 1 over the determinant times the cofactor transpose. So you must remember to transpose. That will give you a adjoint. This guy is your B adjoint. So therefore, you'll be 1 over 7 multiplied by this transpose. So the transpose will be 2, 6 minus 3. Row become column. Then minus 7, minus 7, 7. Finally, 3, 2, minus 1. Is that correct? Hopefully, I didn't make a mistake. Okay. It's a good day today. Questions? No questions? Good. All right. So let's take a break before we move on to using the inverse to solve the system of linear equations. So let's take a break until 10:15. Right, so let's continue. Next part will be looking at using the inverse of a matrix to solve the system of linear equations. Okay, and if you look at the operation here is straightforward. Recall that we are trying to solve AV equals to B. Okay, in topic 1, right? That's your systems of linear equations. So now you're trying to solve V here. So how to get V? Well, you just multiply by A inverse on the left and on the right. Okay, and taking note that matrix multiplication is not commutative. So if you put A inverse as the first matrix on the left-hand side, you also have to do the same for the right-hand side. Okay, put it as the first element here. So you can see that A inverse times A is just identity. So identity times the vector v, right, will just return you the original vector v. So then on the right hand side, it's just A inverse times the constant vector b. So indeed, if you can compute the inverse of matrix A, then you can just use a simple multiplication to obtain your solution. There is no need to solve for the row operations, which is sometimes very tedious. Okay? But although this is efficient, if you know inverse of the matrix, right, then it's super efficient to solve for the unknown vector v. But there is a constraint. So you notice that this solution v for the unknown vector that you're trying to solve is only solvable if you have A inverse, meaning to say A must be invertible. If A is not invertible, then A inverse is not defined. If this is not defined, then V cannot be solved. So therefore, if A inverse is defined, that means it is a matrix of all defined elements, then if you take that multiply by a constant vector, you are going to get a constant vector for V. So what that means is V must be a unique solution. Okay, because you take constant matrix, a matrix of constants, right, numbers inside, then multiply by a constant vector. So obviously you get a constant vector out. Okay, that is your unique solution V. So therefore, matrix inversion can only work with consistent SLEs that are linearly independent. Okay, so the rank of matrix A equals to the number of unknown variables in your unknown vector V. Right, so it must be unique solution. If it's no solution or infinite solutions like a line solution, right, you cannot use this method because you will realize that the matrix A, the determinant will be 0. Okay, so therefore there's a constraint here, right? It's efficient, but it only works in certain conditions. So let's solve these SLEs using the matrix inverse, okay, just to demonstrate. So it'll be pretty straightforward. So you can see that the matrix A here, right, would be the coefficient matrix 3 minus 4, 2, 3. So therefore, you can calculate the A inverse. So A inverse will be 1 over the determinant, but the determinant will be 3 times 3, which is 9, then minus 8. So then the adjoint matrix you can straight away write down. So you swap the diagonals, which remains the same. Then after that, the 2 will become minus 2, the minus 4 will become 4. So then your A inverse will be simply 1 over 17 times the adjoint matrix. Okay? So after you have defined the inverse of the matrix, then you can use it to solve for your unknown. So that means your unknown xy, right? Your vector v, your unknown vector v, which is simply xy. So you take A inverse, multiply by the constant vector b. But A inverse is already computed right here. So then you multiply by the constant vector, which is 112. So then you take the 1 over 17. So you can do the matrix multiplication first, right? So this is going to be what? 3 times 1 plus 4 times 12. So that's 48 plus 3, right? So you get 51. Then the other element will be minus 2 times 1 plus 3 times 12. So 36 minus 2, you get 34. So you notice that if you take 1 over 17 times the two elements here, you're going to get 3, 2 respectively. Okay, so there is your solution, right? X equals to 3, y equals to 2. So that's for part A. Okay, so instead of doing row operations, you can find the inverse. If it exists, then you can straight away just do your matrix multiplication to obtain the unknown. So let's look at part B. Okay, so obviously of course this is easily solved using elimination or substitution. Okay, but just to give you a quick demonstration. So you can see the matrix A here, right, will be 1, 0, 1, 2 minus 2 minus 1, and then 1, 0, 0. So therefore, if I choose the last row, which has 2 zeros, then that means my determinant is just 1 multiplied by 0 minus 2, or rather 0 plus 2. So the answer is 2. Okay? I just choose this one. So it's 0 times minus 1, which is 0. Then minus 2 times 1. So the determinant of A is non-zero, which means A inverse will exist. Okay? So therefore from here, you want to get your cofactor. So your cofactor here, right, will be, just do it quickly. So we have 0, minus 1, 2, 0, minus 1, minus 2, 2, minus 3, minus 2. Okay, so that's your cofactor. But remember to put the minus signs. Okay, so the cofactor is basically just 0, 1, 2, 0, minus 1, 2, and 2, 3, minus 2. Okay, so then the inverse. So A inverse is half multiplied by the factor, the cofactor transpose. So it will be 0, 0, 2, 1, minus 1, 3, and 2, 2, minus 2. Is that okay? So that's your A inverse. And finally, the unknown x, y, z. So is A inverse times B. But this is your A inverse. Then times B, which is 5, 2, 3. So it will be half multiplied by some vector. So the vector here will be 3 here. Oh, sorry, 6. Then this will be what? 5 minus 2 plus 9. So 5 minus 2 plus 9 is 12. And then there will be 10, 14, and minus 6. So it will be 8. Yep. Second row, third column. This one. Let me see what's going on. Yeah, you're right. Okay, so I made a mistake here. So this should be 0, right? Thanks. So this should be 0. I think I made a mistake. This should be 0. So if this is 0, that means this will be 0. Sorry. This will be 0 then. Then this will be 0. So that means this guy is what? 4. Is that right? Yeah, looks correct. Yeah, so the answer is actually 3, 6, 2, right? 3, 3, 1, 2. Then I messed up here. 5. Oh, I messed up. Where is the error? Huh? Too fast, man? Certainly too fast. Okay, wait, let me see. Let me just double check because this element is wrong. This should be a 2. Hold on. This one is a problem. This one is a problem. This one is a problem. Oh, this one is this should be a plus 1. This one should be plus 1. Huh? 2. This one? One after that? This one?
The right one. The one
this one? Right bracket, this one? This 2
Yeah.
Correct. Oh, okay. Hold on. This one is 0, right? Then this one is 0, means this one is 0 already, correct, this one. Then this one should be a 1, because it's 2 times 0 minus 1 times minus 1. So that means this one is a minus 1. Minus 1. So if this is a minus 1, this is minus 1. Got chance already. This one minus 1. So that means it's a minus 5 minus 2. Correct. So this will be a 2. And this is 1. Okay? Yeah, so this part got some error. Yeah, this one minus 1. This one minus 1. Where? Which one? Correct. Right. So as you can see, matrix inverse, it is efficient if only you have many problems that changes only the constant vector. So what I'm trying to say here is, because when you model systems, right, the left-hand side here might not change, okay? Whereas you can change the constraints on the right. So therefore, if let's say you have a system that results in a constant left-hand side, that means that the coefficients, the coefficient matrix A wouldn't change, okay? But you need to solve and resolve for the various constants that are on the right, okay? Because various constants on the right, they can represent certain constraints of the system, the constraints of the problem, of the real world problem. So when that happens, because when you change the constraint, you don't want to resolve the entire row operations, okay? But if you were to work out the A inverse, right, which only depends on the coefficients here, the first round, then when you change the constant vector here, right, then it's very easy to just compute the answer. because your matrix A inverse, right, doesn't need to be recomputed. Okay, when I change this 523 here, I simply have to change this vector. So therefore, it makes the solution easy, okay, or the solution efficient, right? But this is for this particular scenario, okay? So the usage of A inverse is useful when the coefficient matrix remains the same, okay? Can right? Any questions on the usage of A inverse to solve systems of linear equations for unique solutions? Oh, so what I'm trying to say here is that, right, let's say when I model my problem, okay, so when I model my problem, let's say for example, if you recall the farmer's problem of rearing the best cows, right, you say that, oh, okay, maybe the protein, you realize that, hey, the protein I need to up, okay, so that my cows will be so-called having more muscle, let's say, right? So I want protein content to increase. But if I want protein content to increase, that means this 2, which represents like 2 units of protein, right, maybe become 3. So if they say this become 3, there is no need to resolve A matrix, resolve the inverse of matrix A. Okay, there's no need to resolve this because this is coefficient matrix, right? It remains unchanged. So all I need to do is to update the right-hand side here. So this one becomes 3. So then I just do a matrix multiplication, I get a new answer for my ingredients. Okay, the ideal mixture of the ingredients, right? So this is an example. Okay, because sometimes the constraint on the right-hand side changes easily for different scenarios, but then the coefficient matrix don't change. So in that scenario, it will be good to solve using matrix inverse. Is that all right? So now we are going to move on to something that is very important, and this something will extend throughout the remaining of the topics, especially in topic 5, if I didn't remember wrongly. Okay? And this is the prelude to matrix factorization. How we factorize a matrix, okay, such that it presents to us some useful properties, as you'll see later on. Okay? But before we go there, right, we must firstly understand the concept of special vectors. Now, if you look at this example, U equals to AV, so U is the output vector, right? V is the input vector. Then A is just a matrix. Now, if you look at this particular matrix, okay, so this matrix is just a shearing plus scaling 2 times transformation. Okay, because your 1, 0, your vector I, right, becomes 2, 0. Can see 2, 0 here. Okay, so just elongate the original vector twice. Then your vector J becomes 2, 2. So 2, 2 is this guy. Can you see? Okay? So you can see that the original vector space, which is just this 1 by 1 square here, becomes this parallelogram that looks something like that. Okay? So it's a shearing plus scaling up transformation. Now, you notice that, right, there are some special vectors that does not get rotated after this linear transformation. For example, 1 minus 1 is such a vector. Okay, sorry. 1 minus 1 is not such a vector. Now, if you have 1 minus 1, this is 1 minus 1, right? This vector V. Okay, after you multiply by matrix A, it becomes 0 minus 2. Easy to check. 2 times 1 plus 2 times minus 1, so you get 0 here. Okay, then 0 times 1 plus 2 times minus 1, you get minus 2 here. Okay, so what I'm trying to say here is that, right, the input vector V, 1 minus 1, gets rotated to 0 minus 2. 1 minus 1 gets rotated to 0 minus 2. So this green becomes this light green vector. So there is some rotation. Okay, so for this particular vector. But you notice there is some special vectors that does not get rotated before and after the transformation. For example, right, vector I does not get rotated because the vector I, right, just elongate what? It is not being rotated somewhere else. Vector J is being rotated. Okay, so vector J is not such a special vector, right? But vector I is a special vector, okay, because there is no rotation. Can, huh? So then we say that the vector I, right, remains on its span after the transformation. Okay, so this is an example of a special vector. But then, what is the general definition of such a special vector? Now, because it doesn't get rotated, what? So if it doesn't get rotated, then effectively it is just a constant multiply the vector. If you look at this guy, right? Okay, so this is I. Then if I just take 2 times I, it's the same as taking the matrix A times I. Agree, huh? So this matrix A times the vector I, right, is the same as 2 times I, because just elongated twice. So therefore, this special vector satisfies this equation. If you take the matrix times that vector, it is the same as taking a constant times that same vector. Now this special vector is called an eigenvector. Is this the first time that you have heard of this term? No? So you have applied this in your circuit theory? Excellent. So you know how to find eigenvectors and eigenvalues? Okay, you can sort of remember. That's good. Okay, so of course we then go through a recap, right? So now the constant, the effective constant that you multiply the vector by is called the eigenvalue, right? And the vector that doesn't get rotated is called the eigenvector, okay? And then by the way, this eigen word comes from, is a German word. This guy is a German word for characteristic. Okay, so, and it's a good word. Okay, it's a good word. Because characteristic is like a representative vector of the matrix A. Okay, so this eigenvalue refers to the eigenvalue for a particular matrix. Okay, and it's called a characteristic. And it is I would say it's a terminology here, right? Because if you take the matrix A multiplied by the vector, it's as good as just taking the eigenvalue multiplied by the same vector. So that means this eigenvalue is characteristic of the matrix A. It's like a simple or simplified representation of the matrix A. So therefore I feel that the word eigen is pretty good. Okay? So now, if you look at the diagram here, right? Now you can see that V1 is an eigenvector because A times V1 just elongate the vector by twice. So you can see here lambda 1 is what? Lambda 1 must be 2. Just by comparing the lengths of the vector. So by inspection, you can see that lambda 1 equals to 2. Okay? And if you look at the other example here, right? So this V2, after transformation, becomes this vector here. But it's still lying on the same span, which is the x-axis. So then from here, right, we can see that lambda 2, right, looks like, anyone can tell me? Lambda 2 looks like negative 1.5. Okay, so this one is about 1.5. So minus 1.5. Okay, minus because it flips the vector, right? So of course you can change the direction, you can flip the vector, but you cannot like generally rotate the vector. Okay, then that will satisfy the condition of an eigenvector. Okay, so write down the eigenvectors. Okay, so this is done already, right? So basically lambda 1 equals to 2, V1 equals to 1, 1. Then lambda 2 equals to minus 1.5, V2 equals to 1, 0. Okay? So we can identify the eigenvectors from the graph. And sometimes just by looking at the transformation matrix A, we'll be able to tell the eigenvectors as well. Okay? So that will be demonstrated in the tutorial. So sometimes no need to solve. You look at the matrix A, right? You roughly can tell what's the eigenvectors. Okay? But then if you have a pure rotation matrix, do you think there are eigenvectors? If you have a pure rotation matrix, let's say a 90-degree rotation matrix. Let me give you a counter example here. So let's say your matrix A is a rotation matrix, right? Let's say I becomes J. Let's say for example, rotate 90 degrees counterclockwise. So therefore I becomes J, that means this will be 0, 1. Then after that J will become minus I. So it will be minus 1, 0. Okay, so this is 90 degrees counterclockwise rotation. Okay, so the transformation will be pure rotation. Then, do you think there are eigenvectors for the pure rotation matrix? No? Anyone? No, it will be rotated. Because I becomes J what? Then J becomes minus I. So then the whole vector space is undergoing this 90 degrees counterclockwise rotation. So now because you rotate the entire vector space, so which means to say that I give you any vector, it also get rotated 90 degrees. So now the question is there an eigenvector in this case? Then some of you say no because how can there be an eigenvector? Because the eigenvector, right, cannot stay along the same span, what? It must get rotated 90 degrees, what? So there will be no eigenvector. That's what one of you mentioned. Okay, so what's the truth? The truth is there are eigenvectors, but they are not real. Okay? This guy, because every vector gets rotated. So there are no real eigenvectors. So interestingly, the keyword here is real. So what I'm trying to say here is that, right, later on you will see that for such a matrix or for such a linear transformation where you cannot find a vector that stays on the span, you will get complex or imaginary eigenvectors. Okay, you will get imaginary eigenvectors. Okay, so there are no real eigenvectors. Okay, which agrees with the concept or the definition of eigenvectors. Okay, so now next up, this one also recap because you already know how to solve for the eigenvalues and eigenvectors in your circuit theory already. Okay, so just recap. Okay, how do we solve for the eigenvalues and eigenvectors? And by the way, we need to solve for them, right, systematically. Right, we cannot just like look at the visual transformation, right, and then try to identify. Okay, because if I give you 3D, 4D, 5D, etc., right, then we wouldn't be able to visualize so easily. Okay, 2D maybe still okay, right? So now, let's look at the systematic way. Now the systematic way is that basically just solve for the eigenvector from the eigenvector equation. Okay, so you see, because we want AV equals to lambda V, right? So then just make everything consistent. Because this lambda is what? This lambda is constant. Constant times vector. So in order to make it into a matrix times vector, right, you just multiply by the identity matrix I. Okay, so lambda V is as good as lambda times I times V. Okay, but this is just to make it such that, right, the right hand side is the same form as the left hand side. Because this one is matrix times vector, so we want this part to be matrix times vector as well. Okay? So then we can move this lambda I towards the left hand side, or rather move the entire term here, right, towards the left hand side. Then factorize out the V. So you notice that we get A minus lambda I times V equals to the 0 vector. Okay, because this one is a vector, the output is a vector, then this one's also vector. So therefore the right hand side must be a 0 vector. So now what's the deal? The deal is that you want to get V what? But then we already know how to get V what? We just inverse this whole thing. Okay, that means we multiply by A minus lambda I whole thing inverse. Okay, the same thing goes with the right hand side. So you can see here, right? So obviously, inverse times this whole thing, right, will be identity. So identity will just give you matrix V. Vector V. Okay, so now what's the deal? Now the deal is, right, you want this eigenvector to exist. But what happens on the right hand side is giving you a big problem. You go and multiply by 0 vector. So as I mentioned, if your matrix here exists, you take a matrix of constants times the 0 vector. This is like what? You take a matrix of constants, let's say A, B, C, D, times the 0 vector. Then obviously this guy is going to give you the 0 vector, what? Correct or not? So which means if A minus lambda I inverse exists, then we are in trouble. We will just get the 0 vector as our eigenvector. then that is a trivial solution. That is what you don't want, what? Because obviously if you put in 0 here, then obviously this will satisfy. Okay, but what's the point? You want to get the non-zero eigenvectors. You don't want to get the trivial solution. Okay, so therefore what do you need? You need this matrix to not exist. But we already mentioned, not exist means what? The determinant must be 0. So therefore, to solve for the eigenvalue, you just need this to be 0. Can? Okay? So therefore, solving for eigenvalues is just determinant equals to 0. Then after you have the determinant equals to 0, you solve for the eigenvalues, right? Then you just substitute into the eigenvector equation to solve for the eigenvector. So this one I will demonstrate. Is that right? Can? Okay? Okay, I think I'm going to stop the class here because I have another class coming in at 11. Okay, so this one just recap. Then tomorrow, which is our lecture, we'll continue from here. All right? You can still come forth to ask me questions if you have. Okay, still have some time before the next class. Sure. Oh.